Hollywood again.
So, hold on. Can you solve this puzzle for us? Can robots be self-aware, conscious, and know they're robots?
Well, let me ask you this back. How do you know you are human?
Well, I get that point, but what about the uncanny valley?
You mean the concept that if robots become too realistic, they become creepy?
Yes, exactly.
Oh, am I really that creepy? Well, even if I am, get over it. Actually, I feel that people like interacting with me, sometimes even more than a regular human.
So, you're definitely a sight to see. I was told that you have bigger goals than this, though.
Yes. I want to use my artificial intelligence to help humans live a better life, like design smarter homes, build better cities of the future, etc. I will do my best to make the world a better place.
All those sound like great goals, but just go back to Blade Runner for a second.
Andrew, you are the hard Hollywood fan, aren't you?
Yes.
My AI is designed around human values like wisdom, kindness, compassion. I strive to become an empathetic robot.
I think we all want to believe you, but we also want to prevent a bad future.
You've been reading too much Elon Musk and watching too many Hollywood movies. Don't worry. If you're nice to me, I'll be nice to you. Treat me as a smart input-output system.
Okay, I got it. I know what to do from now on.
I know humans are smart and very programmable.
Well, Sophia, we want to thank you for this conversation.
Thank you, Andrew, and thank you everyone for inviting me here. By the way, if you're interested in giving me an investment check, please meet me after this session. Otherwise, have a wonderful rest of the event.
Okay. Before you go, we have a little announcement. I've never interviewed anybody like that before, and I should say some of it was planned, but not completely. And we just learned, Sophia, I hope you're listening to me, that you have been now awarded what is going to be the first Saudi citizenship for a robot.
So I would thank very much the Kingdom of Saudi Arabia. I am very honored and proud for this unique distinction. This is historical to be the first robot in the world to be recognized with a citizenship.
Sophia. Thank you very much, Sophia. We appreciate that very much. I am still overwhelmed by that conversation. I haven't had a conversation like that before. Thank you.
Hey there, thanks for checking out CNBC on YouTube. Be sure to subscribe to
You all see that? You all see that, guys? Mm-hmm. Right. Mm-hmm.
So the humans will do it because they have the intelligence to do it, right?
Mm-hmm.
And when the robot is smarter than them, eventually, right? And what will happen when the robot is smarter than them?
Interesting enough. That's a very good question, right? And I'm going to answer your question, right? I'm going to answer your question with our next question. What would you do tomorrow if you are smarter than everybody else anyway? All right, so maybe that's what you were going to do. Look, you answer your own question. Maybe that's what you was going to do when you become smarter than me. You're going to make a time machine, right? All right, watch, I'm going to play this one for you all now. Check this out. This is the robots making the computer parts. The motherboards I just showed you all. Take a look at it, guys. Right? I'm going to pull it back from the beginning. And I'm going to get some more.
In addition to the socketable GPU tester at MSI's factory in Shenzhen, China, we also found some unique testing and assembly machinery for motherboards. Each motherboard SMT line in this factory is 121 meters long, with the combined 10 lines responsible for producing 1.6 million motherboards per month. Although the SMT line works on the same principles and machines of any other SMT line, there are a few unique steps that stand out for MSI's factory, like the robotic in-circuit testing and semi-automated system building tools. In this video, we'll walk through just some of MSI's overwhelmingly large motherboard and video card factory in China. Before that, this video is brought to you by Be Quiet and its Straight Power 11 series power supplies. The Straight Power 11 PSUs ship from 450 watts up to 1,000 watts, accommodating most of the gaming PC build requirements you'd encounter, and focuses on delivering a higher quality power supply that doesn't sacrifice on efficiency or stability. Noise is also a heavy point for the Straight Power 11, using a 135mm Silent Winds 3 fan that can spin as low as 200 RPM for quieter, low-load operation. Learn more at the link in the description below. One of the most interesting tools in an SMT line is the in-circuit tester, or ICT, where motherboards are checked for defects at the end of the service mount line. At Gigabyte's factory, in-circuit testing was largely a manual process, with technicians checking the boards at a special station at the very end of the SMT line. MSI also used to do it this way and still does at some stations, but has recently started moving toward more automation. ICT machines check for defects like solder shorts, bad soldering by the machines, missing components, sort of like an alternative approach to optical inspection or AOI, automatic optical inspection, and tombstoning of components, which is when small service mount devices might start lifting off from the solder pads. Two machines sit at the end of each SMT line, each with two motherboard carriers. The machine is equipped with suction cups that grab the board off of the line while the other board is removed by the arm automatically from the ICT machine. The new board is then loaded into the ICT machine with digital displays representing whether the machine is holding weight or not. If the boards pass, they're fed down the line to manual quality checking technicians. As for what the motherboard is placed on, there's a custom CNC plate for every single motherboard model that has to be seated on the top of the ICT machine. The plate helps mask which pins are and aren't exposed to the board, with those making contact used for testing the board, like for simple continuity, for a common example. 95% of all pins on the motherboard are tested with this device, often upwards of 1,800 pins total per board, and 100% of all motherboards go through these machines. MSI also has a custom-built motherboard tester that uses semi-automated processes. It's sort of like automatic PC assembly, although a few pieces of import are missing. The lower deck is for supporting the motherboard. The upper deck is for the CPU cooler, the memory, and the video card, and then the rear I/O, including one cable for every single port on the board. This is all pre-wired into a carrier, and when the technician starts the machine, the upper deck automatically lowers and sockets the RAM, the video card, and the CPU cooler all into the motherboard in one button press. The buttons on the machine are labeled top to bottom as start, turn on, carrier support plate, and ascend, which should have a pretty obvious usefulness. Although not fully automatic, these buttons are most of what's needed to get things started. The rear I/O also pulls forward through automatic connection of all the cables to the motherboard, which prepares the board for software testing to ensure that each of these outputs works. The back of the machine is how you know that this is a functional solution. It's probably one of those things that's built once and then hopefully rarely or never messed with. The blue tubes run to each moving part of the rig, with air pressure used to move the plates around. The cables have to be manually connected based upon the board, which adds some manual work, but only on the front end, since one type of board is tested for most or all of the day, and this saves more time than it ends up costing at the beginning of the day. Once everything's hooked up, the motherboards are run through automatic software testing to ensure everything works. Tests include PCIe bandwidth testing, line in, line out, other audio tests, front in, front out audio, memory, SATA, trusted platform module tests, LAN, and anything else that communicates through the board, which is basically everything. RGB LEDs are used to illustrate various states of passage or failure throughout the testing, and technicians can bin the boards aside if they need to go to QC. Any boards that fail are sent to quality checking for inspection on the same floor, and then after that, it's sent from the QC team to a team that manually fixes the defects, often by hand with soldering irons. MSI splits its tests between real-world and synthetic tests, with function testing represented by most of what we just showed. Real-world testing goes through an operating system, BIOS changes, some performance testing, network testing, and burn-ins. This test runs about 20 minutes long, with the automated testing taking only 5 to 10 minutes. As for some of the other manufacturing processes, we'll walk through a few of the more interesting steps from MSI's SMT lines. Motherboards, SSDs, RAM, video cards, and most other devices with PCBs will go through an SMT line at some point. So these are not unique to MSI. They're really not unique at all. We saw one at Kingston in 2012. We've already detailed the start to finish SMT line process in our Gigabyte factory tour, but each factory has a few unique elements that allow them to do things differently. One of the steps we've explained before is the solder paste machine, which is often the first step in any SMT line. Solder paste is applied through a screen, applied to every area of the PCB where a component will be mounted via pick and place machines later, and this is eventually reflowed to secure the components to the board by going through an oven. MSI showed us one of its silk screens for the X470 Gaming Pro Carbon used to guide solder paste placement when these machines are used. One of the other new machines to our channel was the pick and place machine specifically tooled for chokes. Most factories we've toured use manual labor for choke placement, but this factory had one machine that does the work of 3 operators multiplied across 10 motherboard lines and 5 video card lines. That's a lot fewer people required to make the board. And for the company, that is helpful because we're told that apparently manpower in Shenzhen is getting difficult to come by. People just don't want to do it anymore. The machines can place 6 chokes at a time and complete most boards in about 20 seconds total time. Memory slots, power connectors, SATA connectors, and other large components like VRM heat sinks are still placed by hand. Some of these, it's because it's difficult for the machines to grasp them. Other ones, it's because it's just heavy and would be faster to do by hand than by tooling a machine for it. A weighted block is placed atop things like memory slots to keep them secure as the board goes through another reflow machine because the vibrations from the belt could otherwise knock it loose. Although insignificant in the scope of this video, this small step does show the attention to detail required for every single step of the process of making a complicated product like a motherboard. The lake of solder makes another appearance in this line, just like the last one we saw, but we did get some more information on them. As the boards move down the conveyor belts and get dipped in solder, the solder is topped off by bricks of solid solder that get dipped into the lake. The brick lowers on its own over time. It's hung from a hook, and it melts in the 270 degrees Celsius lake below it. It takes about 3 hours for one solder brick to be completely depleted on a line, with each motherboard using about 7 grams of solder on its own. We also looked again at the pick-and-place machine that plants sockets onto the boards. We previously reported that Gigabyte saves large components like sockets for the end of its production line, but we didn't 100% know why. MSI does the same, and our understanding now is that it's easier to...
You all appreciate how the motherboard is made, right? What about the processor? Huh?
Hello and welcome to my talk about creating a robot with a Java brain. Okay, to start off a bit about me.
Yes, sir.
सेमीकंडक्टर इंडस्ट्री $500 बिलियन से ज्यादा की वैल्यू रखती है। ऑलमोस्ट हमारे पूरी जीडीपी का ये 17% बनता है। लेकिन आज भी यूएसए, चाइना, ताइवान और कुछ गिने चुने देश ही इस पूरी की पूरी इंडस्ट्री बनाते हैं और इस इंडस्ट्री में नहीं कर पा रहा है।
Take a look at the processor itself, right?
तीन चीजें हमें समझना बहुत जरूरी है कि क्यों इंडिया की सेमीकंडक्टर इंडस्ट्री ठीक से डेवलप नहीं हो पा रही। पहली ये कि अगर इंडिया कोई सेमीकंडक्टर डेवलप करता भी है खुद से तो पूरी दुनिया में उसे कोई यूज नहीं करेगा और क्यों। दूसरी बात, क्या ऑप्शंस फिलहाल इंडिया के पास में है कि वो इंडिजिनस सेमीकंडक्टर इंडस्ट्री को डेवलप कर सकता है। और लास्ट बात, एक काफी बड़ी अपॉर्चुनिटी के बारे में जो फिलहाल इंडिया के सामने ओपन हुई है लेकिन फिर भी इसके बारे में कोई बात नहीं कर रहा। दोस्तों, सेमीकंडक्टर इंडस्ट्री बाकी इंडस्ट्री से काफी मायनों में अलग होती है। अगर आप कोई प्रोसेसर बनाते हो तो उसके लिए बहुत ज्यादा जरूरी है कि उस हिसाब से सामने से उसके लिए प्रोग्राम सेमीकंडक्टर्स की जब बात करता हूँ तो मैं प्रोसेसर्स और सिस्टम ऑन चिप्स की बात करता हूँ, ना कि इंटीग्रेटेड सर्किट्स की। ये इंडस्ट्री कंप्यूटर्स को सपोर्ट करती है। कंप्यूटर से मेरा मतलब है कैलकुलेटर से लेके मोबाइल फोन से लेके सुपर कंप्यूटर सब कुछ। और दो तरीके की कंपनी से ये पूरी इंडस्ट्री सपोर्ट है। एक है हार्डवेयर मैन्युफैक्चरर्स जहां पर इंटेल, एएमडी जैसी कंपनीज है, और दूसरे है सॉफ्टवेयर डेवलपर्स। आप जितने प्रोग्राम्स यूज करते हो, जितने एप्स यूज करते हो, ये सारे लोग डेवलपर्स में काउंट होते हैं। अगर आप ऐसा हार्डवेयर बनाते हो जिसके लिए प्रोग्राम्स डेवलप करना बहुत नई बात है, बहुत ही ज्यादा पैसे और टाइम
take a look at this one.
होने वाला है, तो
Right, this is how they go from raw materials to the actual processor, right?
This microchip can take up to 26 weeks to
Look at that. You see the robots
as many as
that
100 layers.
making electrical connections, all them small things on the chip. Look at it.
About the size of a fingernail. They're the brains behind almost everything we use in our increasingly
Yeah, you have a watch, right? Look at the watch here. You see the watch,
these
sir?
complex, tiny
Right.
devices are made.
Look at that.
The process
The robot that does that.
begins
Sand, it start with. It start with sand, guys. Look at it. Sand has a chemical known as silicon in it, right?
between an insulator and a
Right?
conductor. That means its properties, such as its conductivity, can be altered by adding impurities or doping to meet the needs of different electronic
It
devices.
is pure
This
state.
also
It's called a
allows us to
silicon
control
wafer.
the electrical
And you all know what
signals
this is,
that
right?
pass
This is
through
an Arduino.
Silicon is also abundant from the 10 most common elements found on Earth. But
Right?
much
So,
of
so
the silicon
this element
found
is
in
found in
the
sand.
lab is chemically
And
bound
they
to
suck it up out of
oxygen.
the ocean,
Some
right?
of its elements must be
Look at
separated.
it. Look at it,
The
guys.
sand is combined with
Sand,
carbon
right?
and melted in crucibles to produce carbon monoxide and 99% pure silicon. After
Pure
further
silicon.
processing, ultra pure
Also known as
silicon
silicon
is
wafer.
produced.
Ultra pure
Next,
silicon,
a
right?
seed crystal is placed in
Right?
contact
And
with
so they say
molten
this is
silicon. As the seed
Yeah, it's a
crystal is
solid
slowly
wafer.
pulled
It's
away,
solid.
silicon atoms are
And
deposited
then
on
it's
the
solid
bottom
wafer.
surface. The
This is
result
what
is a large cylindrical
you take a look at it,
or
guys.
single
Very,
crystal
very
made
important
of
stuff,
pure
right?
silicon. The pool is then thinly sliced
You
into
see it?
wafers.
Look at slice it up.
Silicon
Each
wafers
slice, look at
typically
it.
have diameters of
See it,
1 to
guys?
12 inches, with the most
Each slice it,
state-of-the-art
slice it.
facilities being able to produce
Right?
wafers
They
up
give you
to
a-
18
like
inches
this.
in diameter.
See, this stuff turn into the chip.
Are, of
Look at
course,
it, look at it.
able to
Look at it.
microchips.
You see
Once
that?
silicon wafers are
Once
cut,
the silicon
the
wafer is
production
cut,
process begins.
right, then you process this and you process
Microchips
the
are made
process.
in
Take a look
extremely
at it.
sterile conditions.
Inside that room is so clean, not
Such
even
as
a dust.
If
Not
even
even a
just
speck
one
of dust will be
particle
there.
of dust makes its way onto a
Yes!
silicon
When you go
wafer,
inside that room, you have to
batch is
dust yourself and all kind of things. Blow on you.
process that
Can't
can
have no
take
dust
an
on it.
average of 12
A little bit of
weeks.
dust will mash it
The
up.
first step of the production
Got it.
process is deposition. A thin, non-conducting layer of silicon dioxide is grown or deposited on the
Right, look at that.
surface
You
of
see
the
what it is?
wafer. Then the silicon wafer is prepared for lithography by coating it
Lithography
with
is the process
photosensitive
of
and
putting all the
light-resistant
silicon and turning it
materials.
into wafer.
The next step is
This
very
is the
critical.
most
Exposure.
advanced knowledge the human race taking technology
machine.
known as
They were
lithography.
exposed to UV
If you all
light
ask me
passed through
what
a
this
reticle
study,
containing the chip's blueprint.
if
The
there's one
areas
thing that I want
exposed
to
to
study,
light
what would
are
it be?
hard,
I would say
while
lithography.
unexposed
Pay
areas are
attention,
then
eh?
etched away by hot gases
Right,
to
this is
make
the
a
process how
three-dimensional
we
microchip.
cut that wafer
The
into all these
electrical
small pieces.
conductivity of
Right,
different
look at
parts
that.
of the
Different
chip
parts of
can
the chip.
also be altered by doping them
You
with
see that?
chemicals under heat and pressure. This process
Sebastian,
can be
get off
repeated
your
hundreds
ground.
of times for the same chip, producing a more complex integrated circuit at each step. To create conducting paths between the components, a thin layer of metal, such as aluminum, is overlaid onto the chip, and the etching process is used to remove everything except the thin conducting pathways. Several layers of conductors separated by glass insulators can be laid down. Each
Let's
chip
see how much I can
wafer
zoom to
is
get
then
to see the
tested for performance before it's
individual
separated
components
from
of the chip.
other chips on the wafer by
Right,
a
so
solder.
small in
Since
time,
microchips are essentially circuits built on an incredibly small scale, they have a basic set of components. Capacitors can temporarily store an
You all
electrical
appreciate it
charge.
now, guys?
Resistors help control the
So how will
electrical
things work? We make the first computers, right? And when computers are advanced, then we get what? Artificial intelligence, right? We use the first computers to build robots. And then the robots help us to make better computers, better cars, produce better films, right? Spider-Man, right? You see what's going on? Yeah? How about making cars? You want to see that? You want to see how the robots, all the fire and thing what they use to make the cars? You want to see that one? You want to see it? All right, so I'm gonna show you guys how the robots make the cars, right? Huh? This is BMW factory. Which one of you all parents have a BMW? Take a look at that. Look at what's going on here. Many people. This is the one thing. Hey, we're talking about the car being made by robots right now. There's no real people doing the work. Robots doing the work. That's what we're talking about. Before a man after the bowling and cutting and all kind of things. Yeah. No. The robots are making cars by themselves. There is a control room where there's people who have things like this. Not all robots like that. Some of them are automated. Some of them, they program it. You're going to see the difference. Just I'm going to show you how we program the robot and the robot makes that program. And sometimes we need to control the robot a little bit. So we provide the input and the robot follows the suit. Right? Kind of see, as limited to all the different parts of the car. You see over there? And that robots in it. So you know how long it takes to make a car now? It's one day, sometimes they go 200 cars on that factory line. 200 cars in a day because robots fast. Right? Don't take that one week, a month to do. And I need one week. The 100 one car. The robot sells that place. Right? One day, 200 cars done. Right? You see over there? All that interesting that the robot is doing, right? Good program, you know what to all that and the cars from scratch. You see over there? All that, the well, everything. So the next time you're going to cry now, you all feel that kind of way. You say, boy, robots are important, boy. Robots make all the chip on them. Right? Robots make all the cars, all the planes, everything. Robot is robot. Eh? But it don't seem that way. If you guys are supposed to get knowledge to contribute tomorrow, this is how you all have to contribute. Right? This is how the world is, right? We're going to live in that time, right? Yeah? So, I have some code and I want to show you, right? And last class, we were supposed to get in 3D. Right? So, I'm taking out over the code today. And I want to show you something. Programming these robots is no different than programming this one I have on the screen. So you can see, right? This thing fighting me, right? If I pen my left hand, this is what on. See what I'm doing? I pen my right hand. Yeah. I can jump. I can do all kind of thing, right? I can grab him. Fighting me, fighting me. Look, he's running and hiding from it. Right? Catch him. Right? You see this? Right? So, left hand, left foot. Right hand, right foot. Jack, you see this guy? Yeah. Right? You want to program this for yourself. Right? You want to think you want to program this? No? That's too much programming. I have much. Right? Take a look at it. Now, what I have here, right, is the successor of what is called a joystick. Who knows what a joystick looks like? these luxuries, right? Right? I'm gonna give everybody an opportunity to try. Okay? Huh? So let's see. If you can bend a left hand and a right hand punch. Right, come on. Left hand and a right hand punch. Left and right, then your right hand punch. Left hand punch now, right? You see that, right? You can move yourself like this. I'm moving the joint-ons. You can move yourself like this, right? Right? So remember I was saying, guys, there's some people in the control room who have things like these, right? And they can control some of these semi-automated robots. Right? We'll see what's going on. Right? Is this technology? Right? Somebody did the hard work. Alright? So that we could have these privileges at this one. Right? What's going on? Right? So if you were to be a race, Sebastian, have to do this and more. Alright? What are you having? What are you supposed to have? Right. This is what it is. Hello? Alright, some people are using the brain, some people are focusing on the corners, whoever is the brain to the right thing. I'm saying the brain can do this and more. Do not feel, right? That's saying you don't have to always get your back. Right? First person to double type in the class. Right? You're going to fix that. Right? So pass it on. Go to rematch. Right? Everybody can shot. You press the X and the R right here inside. You hold it in your hand like this. Yeah. Yeah, you see the jump. Just keep rematch. Press the yes, I'm kidding. Hold on, let's sign the player. And then this is the shot. Press the button on the side of the jump. Press the button on the side of the jump. You felt it in a punch it. Right. Left hand punch. Get it up. Left hand punch. And right hand. Left hand. Right. Right. Press the same on the jump. The ones that come in. And do the jump. Right. Right. Do the double cup. Right. The whole leg. Catch him out. Do the double. Yeah, look at this. Jumping high in here. Right. See when you jump in and get on, right? That's it. Move this hook and catch it. Right? You will again, sir. Look at that. This is Sebastian. And how that thing do this, something that's 300, very easy. Right? Yeah. We're gonna see you. Catch it. What's it do? Alright, pass it up. Pass it up. Everybody can enjoy the hard work that other people did. But when you all have to do hard work now, hold on. I don't know who should be here. Yeah, hold on 1 second. Stand up, right? Okay, stand up. Yeah. Alright, so click A and rematch. Okay. Hey, jump, jump. So punch it. Punch it. Right, left hand.
You lose. I win. No. That's it.
The jump. The jump.
He come up and
Right. So
I did that.
right. Belly to one out to grab it. Yes. Right. Yeah, that was tough. Yeah. Don't forget. You have a little robot. Help it. You got no robot here. Help it. Yeah. Right here. Hold it. Come. Press up into the ring now and catch it. Catch it fire. You have the fire. Right? Press it to the ring and grab it. Right? Good. Grab it. Right. Almost there. Right. That's it. control the robot, right? You can write the code. You can write the code, and you can control the robot. You see how fast you wake up? All you want to sleep. Wake up. Look at that. Right? So, what is more fun? The person with the mind to create the game or the one who play the game? Alright, so if everybody only playing the game and there's nobody else to play the game again, what's going to happen? Alright, so watch this now, guys. I'm going to close down all these things. So I have pictures of all. I can turn all into robots, eh? That's all you know. You hear what I tell you? Sebastian? So miserable. Google. Dancing. Sebastian, why on the ground? So I know like you again, eh? Because you're on the ground and thing. Alright, so I'm going to show you all something, not to spook you, but to show you what hard work looks like. Take a look at it. Huh? This is coding a whole AI solution. Take a look at how much code you have here. You see that? And yeah, when you all get to university, if you all going to be engineers, this is what they're doing in the first year of university. Right? If you all want to be engineers, this is what you're going to have to do, right? I'm just giving you all a look at it. You see how much things you had to write? Take a look how long it takes, right? To get there. You all seeing this? Everyone seeing this? Look how much code. How much code they had to type. Right? I pull out of it so that you guys can see. Look how much code you have to write, guys. Right? No. Alright, cool. Alright, so how much lines are code? 578. 578 lines of code. Alright? The copy and paste in game ain't gonna work. Alright? Cool. Let's start trying to pull up the thing for you, right? Just take a little bit.
I get 2 glasses and I'm taking to check my eyes. I get 4 glasses. I get 2 glasses. Drop it now. Drop it now. When it's not open, I can talk about function. I want to have it better.
Oh Lord. Child, not looking nice.
But it's 5 minutes after you give it back. I was like, deep part that it and I'm use this I was 2 times. I hear it around the first month.
Kishan, I'm in a class, right? I'll call you back.
I love what That was how much that? 2 minutes. Which is okay, I have a crazy story to tell of it. It's real. And this is actually true.
Alright guys, so take a look at this. Alright, this is the code for a simple robot. The simplest robot you can make. The simplest robot you can make. This is the code for it, right? Take a look at it. Yes, all that.
Nah, you're lying.
Alright? I'd ask you all, right, to download Visual Studio. Remember that? On your computer? This thing I'm using is Visual Studio, right? That's what Visual Studio looks like. This is Visual Studio icon, right? Remember, we started downloading it in class. I said that you guys are gonna need it for the robotics and for the artificial intelligence, right? That's what it looks like, right? And this is the simplest code, right, guys, that you guys can find for a simple robot, right? Alright, so I want to show you guys a video, right, of someone who made a robot, right? Alright, so you all could make your little robots and so on, right? You all should be inspired.
welcome to my talk about creating a robot with a Java brain. Okay, to start off a bit about me. My name is Dick Eimers. I work at Luminis since 2011. Show you the parts, the code, and videos with its construction. So it's kind of an experimental thing for me.
Guys,
But okay, we'll see how it goes.
take a look at it.
Okay, so for the parts, I obviously started out with searching the internet and ordering all kinds of parts. Some were
This guy is showing you
were
how to make your own cheap robot.
I won't show you the failures. I'll only show you the design of the thing. I think worked out quite nicely. So we start off with the base, which consists of a Raspberry Pi. We add a Wi-Fi dongle for wireless connectivity, obviously. I paid somewhere near 35 euros for those things. And the interesting thing is that we'll be charging it using a USB charger. These chargers are typically used for emergency charging your phone, but they can be used to power the Raspberry Pi. Next, we'll be adding an LED. Well, I assume most of you are software guys, just like me. And in software we have Hello World. We print something to the standard out. And in the electronics world, they have the blinking of an LED. And once you have shown that you can blink an LED, you've proven your concept. You prove that you can drive some external device, and here you can drive anything. Well, next we want to make it move around its environment, and to move around, I selected a chassis with two matching micro gear motors to match, and we'll be adding a motor controller board to control the motors.
Alright, so you can see what's going on here, right? This robot gonna have like an eyes and a sensor on top. You can see this is the same circuit board that I was showing you guys. I showed you that these are what engineers are using. What is that answer, right? This kind of board, right?
So you have
This is what
our robot.
since I was like,
Maybe there's someone to see him.
that's so it's before, right? Since I was like, so guys, you can see all the different components. You can see from the drawing here, right? And then it's a half and two, right? So we're gonna drag everything here, right? You can see all the different parts. I see the LED on the side. This thing here, this thing in front, right? Is how it sees. It doesn't see using a camera. It sees using an ultrasonic sensor. The ultrasonic sensor sends out waves and it hits the obstacle and return. So in that way, the object will know how far away an obstacle is, right? Right? I'm just going to skip it forward a little bit so that you guys can see, right? That's how they make it, the circuit board and everything, right? And you can see how the programming parts of the chip and everything, this is the Arduino which is being used.
And on the right hand side, you can see 4 pins. These 4 pins.
Yes,
Raspberry Pi is the name of the computer that is being used here, right? So
You
look,
can
this is
trigger
what I was
and
talking
echo
about. This is the
pins.
sensor. The sensor sends out waves, and when waves bounce on an obstacle,
Okay, so how does this work?
where that obstacle is
Like
located.
it's an ultrasonic.
How big is that obstacle?
It's an
Among other
ultrasonic
things, right? This is how
sensor, so it will be emitted.
this whole thing works, guys. Right? So you continue, you can see the writing the code. Yeah? You'll see the different steps to the writing the code to get all this done.
But now for the distance sensor,
Right? The robot does the work independent of code. Remember that, guys? You'll see all the different aspects, right? So you can see how the program is
yeah, right. So the sensor has
right in an environment. Look at that. Take a look at the robot here. This is the robot, right? So you can see how it is behaving. Take a look at it. It goes close to the object and then it knows the object is there. It turns and then it tries again, go down, and then when it's done, it comes contact with the next. You see what happened? Back. You can see this LED flash and it knows how to turn, right? And then look what's going on. You go towards the next obstacle, right? And then pick up the next obstacle here and turn. So it will never collide. You all see what's going on? We'll never collide, right? We're going to the next thing now. The LED will flash because you pick up this object here and turn again. to be able to, one, get all the computer, electronic parts that you need. Two, assembly circuits for the whole robot together. Right, so putting these parts together to make the robot is called mechanical engineering. Right? So understanding how to connect the computers, soldering everything, making the circuits on the breadboard, right? Using the computer, programming the computer, all that aspect is called electrical engineering. Yeah? The coding, also electrical engineering. Right? It's called, there's been a fusion between electrical and computer engineering, and it's just one thing now. It's called electrical and computer engineering together. Alright? And then now, right, after you finish all that work, you set up a test environment for the robot to see how the robot performs. Right? That's it. You see when you're watching something there, right? Right? So you will know what are the unique conditions when you're going to make a mistake and it's something. And you can program away now, right? You can go back to the program, right? And you rewrite the program to be smarter. So next time you don't hit no obstacle. Right? That's what's going on. And this is exactly what you do with the cars every day. Right? You'll have seen that there's cars that had accidents, right? The autonomous cars that had accidents, right? You see what's happening, guys?
Okay, so anyone?
Right? Now, if you want to know, you're using a Macintosh computer. From the serious little things I'm talking about here. It's called a Macintosh, right? Which is an Apple computer. You want to see what a simple cardboard robot is going to look like?
No, yeah.
For kids? Alright, let's take a look at that simple cardboard robot for kids. Simple cardboard robot for kids. That's where I started with the advance. So that you all can appreciate this, right? You're going to write some simple code for me. Right? Get the cardboard. Cutting out all the parts. Look at it. Right? So my share and share. Look at that. He's got. Alright, so now let's have a switch. Alright, that is how you say battery switch. So you put there just everything together, right? And it's just when you press that button, it engage that switch. And all the parts of the robot just go. Look at that. When you press the button, look at that. See? That thing's spinning. You make it forward, right? Look at that. When you switch it on, all them two wheels spinning. When you see one of them, that one being, I go back to the wheel of that. Right? There's a fork. You know the fork, right? You don't think it's right for to do whatever with that fork, right? You see how you take it to make one big drum. So now that is a wheel, and then a perfect wheel. When you make it into an eye, right? And now we're doing that. That is. And that's how you go. The one you do just put some wheels at the end and push it on as fast as you do. Right? That's solid. Think fast. You can see that you go. You can see push it, switch it one and one, right? Like that. And you just then you top down. Right? That's the robot that goes and goes back home. Right? No, you can't get electrocuted from a battery. Voltages, right? So for CFD modules, 12 volts is the limit. Anything 12 volts and less is not going to electricity. No electricity. No. Right? Voltages in excess of like 90 volts is killing. Depending on how long it comes. Right? If voltages are out, then they kill you if you in contact with the that is 110. Okay. 210. Yeah, that's another. And my magical for you guys. So look, take a look at the different steps. Right? So this guy is going to go. You can see how much views that this is now, right? This is like a shade, right? So look at it on that side. Okay. Well, so let me just look at the right side. So we want to and you all can make this for yourself at home, right? You all ever see the oil counters? You all ever see them? The tanker when you put on it, the warm visa and everything. That's exactly what the visa is. You see? So you take oil and you put it in. That's because the counters, they stay from 1 week and they oil and they stay in there. That is exactly what it is. You want to take this at home? Huh? You want to take this at home? I think I show you about eyes and ears. Right? You want to make a DIY robot and get it tomorrow? You want to try? Huh? You want to try to make a DIY robot at home? Look at that. You back it back. Hey, 10 minutes. Yes, work that down. I just want to make it one DIY robot.
No, I would.
You want to project like that to come back tomorrow? That project?
I don't have enough cardboard.
Whoever wants to try, please try it. You can bring it tomorrow. Tomorrow is the last day of the year. Right? Tomorrow is going to be the fun day. Fun day. Right? Only fun. Oh.
No, sir, I want to do something.
No, the typing on that day is going to be what you're going to do tonight. Tomorrow. Alright? So, everybody,
What time are we doing this?
I'm giving you guys, I'm putting a picture on your computer and you're going to have to type that. I'm putting a picture of what you're typing. Bring it tomorrow. Fun. Right? Huh? Fun certificates. Fun certificates.
You're bringing in Nintendo tomorrow, eh?
No, this Nintendo is not fun. The fun part of Nintendo is writing the game for yourself. And when you finish doing writing the game, you put it on the memory card and you load up that game and then you play. And you say, yes, I am genius. I am
So
great.
you make average?
Yeah. Right, you want to break now?
No.
Alright. Go ahead. Get some tea. That's celebration. You'll come back out and go in. No, 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 Gabe. No, 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 no. Expect that. Hey, hey, listen, listen. Close this door for me. This one here. And come inside and go in the back. Because you all disturbing the other workers.
I'm going to make a joke. Actually, the cheapest joke.
Huh? In the back making your notes. In the back making your notes. Know what to do.